Guten Tag, mein Name ist Aleksas Mazeliauskas. Ich freue mich sehr, heute meine Forschung mit Ihnen teilen zu dürfen. Und bevor ich damit anfange, ich wollte mich kurz persönlich vorstellen. So, ich komme ursprünglich von Litauen, einer der 3 baltischen Länder. Und mein akademischer Weg hat mich zunächst zu Großbritannien geführt und dann in die USA, wo ich promoviert habe. Danach bin ich nach Europa zurückgegangen, erst in Heidelberg und dann in Cern, in der Nähe von Genf. In 2022 ich bin sehr glücklich, der Emmy-Note Forderung von deutscher Forschungsgemeinschaft von meiner Nachwuchsgruppe erhalten. Und seitdem ich bin im Institut für Theoretische Physik am Philosophenweg tätig. Wenn Sie wollen mehr über meine Arbeit und meine Gruppe und die Forschung zu wissen, hier steht meine Website. Okay, for scientific part I switched to English. So, what are the fundamental constituents of matter is the question which, bothered people for many generations. And now we know that all the matter that surrounds us is made of atoms, very small, tiny particles. They're so small that even in a cup of coffee, you have billions upon billions of them. And atoms themselves are combined of a positively charged nucleus and negatively charged electrons. And electrons and nucleus are bind together by electromagnetic force, and the atoms themselves can combine in molecules and create all the matter around us. So all the properties of density of matter, the fluidity of water is all determined by this electromagnetic force. But if you go deeper, if you look inside the nucleus, which is very dense and contains most of the mass of atom, you find that it's composed of other particles called protons and neutrons. Protons are positively charged and neutrons are neutral. And different combinations of protons and neutrons make different elements, and that's how you get different chemicals in the periodic table, although they're all made of the same protons and neutrons. And around 50 years, scientists understood that protons and neutrons themselves are not fundamental particles, but are made of even smaller particles, which are called quarks, and they are combined together or bind together by kind of a glue, and the particle aptly named is a gluon. A gluon is a representation of what is called of strong nuclear force. And this is the force responsible of protons and neutrons combining together. And it has to be a very strong force because positively charged protons would just push against each other and fly apart. And understanding the strong nuclear force and how quarks and gluons behave is my research. Now, it's very difficult to study these particles because they bind very tightly inside protons. So how do we free quarks and gluons? How we can study their properties when they are not bind? For that, we have to melt nucleons in what we call quark-gluon soup. So if you take ice, it's easy to melt into water. You just heat it above 0 Celsius, and you get liquid water. The nuclear binding is so strong that you need much higher temperatures, incredible 1 trillion Celsius degrees to melt the protons and neutrons in constituents, quarks and gluons. For comparison, the core of the sun is just 10 million Celsius, so with very high temperatures. How can we achieve such an extreme high temperatures? One way is if we were able to turn the time back and go at the beginning of the universe. So around 13 billion years ago, our universe started in this very dense, very high temperature Big Bang, which was immediately started expanding and cooling down, and is expanding up to today. And it's now, our outer space is very cold. But just a microsecond after the Big Bang, the entire universe was so hot and so dense that protons and neutrons couldn't exist, let alone atoms. So everything was melted in this quark and gluon soup. Now, we cannot easily turn the time back, so it would be nice to have a way in a lab to create these very extreme conditions. And there is a way. You can take a nucleus, better large nucleus like lead. Lead is the largest stable nucleus, and contains around 208 protons and neutrons. So, many more than a single proton. And you can collide them at very high energies and hope that this will melt the nucleus into quarks and gluons. So think of about two ice snowballs where you collide at very high energies. This kinetic energy will convert into heat and will melt ice, and for a short time you will have liquid water. But this water will expand, cool down, and will be converted again into ice or snowflakes. This is kind of what happens when you collide two nuclei at high energies. It melts, this nuclear matter melts for a short amount of time. It expands, cools down, and quarks form again various particles like protons and neutrons and pions and other particles. And thanks to this famous Einstein formula, the energy can be converted into mass. So if you have a lot of initial kinetic energy, you can produce many more new particles, much more than just 208 neutrons and protons. So really we kind of melt the matter and reconfigure it into new particles. Now, how can we achieve such high energies? For that, we have a CERN Large Hadron Collider, the most powerful particle collider in the world. So this is not close to Geneva, at the border of Switzerland and France. And the around 10-kilometer ring is around 100 meters underground. And most of the year, it accelerates proton particles and to discover, to do high energy research. However, around 1 month per year, it collides with lead nuclei. And these collisions happen in 4 interaction points where the big 10-meter or like building-sized detectors are built. Because after this collision, here at the center, it's like microscopic collision, produces thousands, tens of thousands of particles. And in these huge detectors, these particles are measured in these little white lines. These are tracks of particles. And from these remnants of a collision, we can try to reconstruct what are the properties of this melted nuclear matter. So here is the example how different collisions look in a detector. So each line is an individual particle after the collision. So the collision happened, produced a lot of new particles. And if you have a small collision, like 2 protons colliding, you see a bunch of particles in the detector. But if you take the largest, like 2 lead nuclei, they produce tens of thousands of particles. So it's really a challenge to individually track all these particles. Now, as I mentioned, in that collision, we melt nuclear matter in quarks and gluons, which expands, cools down, and we see these remnants particles. So from studying these, the trajectories of these particles and different correlations, we can tell about the property of this matter, even though it exists for a very short amount of time. And I will skip the technical details and just present one of the main results, which was quite surprising, is that this tiny droplet of melted nuclear matter behaves as a very good fluid. So how do you kind of differentiate how good a fluid is? So there's a property called viscosity, which you can imagine, a honey dripping is quite viscous. It doesn't flow very well. So material which has small viscosity flows much better. And kind of in physics formula, viscosity is quantified with coefficient eta, which tells you how much force you need to push against the fluid. So the bigger this viscosity, the harder the fluid resists more. And if you compare different fluids, for example, water, it's very good fluid. And what is good to compare is viscosity over density. So this is the graph of this viscosity over density. And water has certain value. And maybe you have heard, if you take helium gas and cool down, it becomes liquid, and even we call it superfluid. And the superfluid helium has very low viscosity. It has much smaller than water. However, the research done at CERN and also in US has shown that if you look at the this viscosity or viscosity over density for this quark-gluon plasma, it's even smaller than superfluid helium. So although we have a very small droplet of this nuclear matter, it behaves as incredibly good fluid, which we call almost perfect fluid. So this is sort of a big result from our field. And now just briefly to mention what is my own research, how I'm contributing to this better understanding of nuclear properties. So these collisions are very violent. When two lead nuclei collide, they collide almost at speed of light, so like here. So after that, you don't just get a nicely sitting droplet of matter. It's expanding violently, and it's very far from equilibrium. So it didn't have time just to sit and kind of calm down. So the collision is very violent. So between the initial collision and a stage of the matter where you can talk about this fluid expansion, there's some evolution. And I don't want to go in details, but now we have understanding of different stages, how you go from the nucleus collisions through various stages until this fluid. And my work was mainly to try to understand this so-called equilibration process. So I'm studying how this very far from equilibrium initial state equilibrates using different numerical and analytical methods. So, and the result from this research was that this equilibration time is very short. If you express it in seconds, it's 3 × 10⁻24 seconds. So it's 3 yoctoseconds. And this is necessary because the entire collision or this phase of quark-gluon plasma just takes around 30 or 100 yoctoseconds. So you really need this fast equilibration for even able to talk about this new form of matter. And we have this very fast equilibration in these collisions. So in summary, these heavy ion collisions are the unique tool where we can study strong nuclear force, especially this interaction between quarks and gluons. Nowhere on Earth we can create these extreme conditions. And our study allowed to understand that this new form of matter, which we call quark-gluon plasma, has very interesting properties which people were not expecting, and that at these high temperatures and densities, the matter can behave as a fluid, and actually even the most perfect fluid known to humankind. And this research, although it's fundamental in nature, allows us to understand how systems, very complex systems, evolve, and there are even connections to other fields. Also here, the collaborations with experimentalists working with ultra-cold atoms, which also study how complex systems equilibrate. So we can share this knowledge and better understand how the systems equilibrate and thermalize. So with this, I finish my talk, und ich bin offen gerne für Ihre Frage.